Okay, so we are going to continue working through lecture set 13 today. So just going to date this, so this is the 29th. All right, so in lecture set 13, we are talking about linear regression analysis, but we have extended our study of regression analysis to multiple, or to the case where you have more than one predictor that is being used to estimate or to model the relationship with the response. So essentially what I'm trying to say is in lecture set 12, we studied simple linear regression. And in simple linear regression, we had a response variable, which was y, which we call y. And we said this response variable is linearly related to an explanatory variable that we call x. So we had one explanatory variable in the system, and that's what made the system a simple system. So simple linear regression refers to the fact that we have one explanatory value. In lecture set 13, we have defined the general regression model, which we also call the multiple linear regression model, where multiple refers to the fact that you can have more than one explanatory variable in the system. So we can model the relationship between y, which is our response, and any number of explanatory variables that are available to us. We started off by defining the general model where you have y as a function of each explanatory variable individually. So we basically said, check to see if y and x1 are linear, y and x2 are linear, y and x3 are linear, etc. We also, in doing that, talked about how we can interpret the parameters of the model. So we're now going to have multiple slope terms. So how do we interpret each of those different slope terms individually? We talked about utilizing the model for prediction, for example, and then we talked about evaluating the model. In evaluating the model, we returned to the coefficient of determination, which was our R² value. And we said, okay, this is a good measurement, except that we know R² is always going to increase every single time we add an explanatory variable into the system. So let's adjust the R² so that we still get the interpretability of the value, but we don't have to worry about it improving each time we add an explanatory variable into the system. And the benefit of this is that we can now use the adjusted R² as a tool for comparison. So we can use the adjusted R² to compare two different multiple linear regression models that are fitted to the same data set, for example. After we finished discussing the general multiple linear regression model, the other thing that we mentioned was the evaluation of model fit. So the model utility test, which was an F-test for the multiple linear regression model. So we went through an illustration of how to construct the F-test, how that F-test acts very much like an ANOVA in that it basically says all the slopes are 0 against the alternative that at least one slope is different from 0. Okay, and then we used that F-test to basically determine if there's statistical evidence that the model is useful. So we have inspection of the pairwise plots. We have values like the adjusted R², but then we also have a formal hypothesis test that we can use to assess the usefulness of the model. After we completed that study, we started talking about an extension of the general multiple linear regression model, which is the multiple linear regression model with interaction. Now we are studying only the simplest case of interaction. So in our illustrations, including the one that's currently displayed on slide 20, we are considering a system where we have a response variable and we have two explanatory variables. In this case, we can consider an interaction term between those two explanatory variables. In the last class where we had lecture, which would have been last Wednesday, we looked at illustrations of the effect of interaction. So we basically determined that what interaction does is play a large role in the slope or the relationship of y with respect to either of the two explanatory variables in the model. So we looked at situations where we held one of the explanatory values fixed, and then we saw the influence of the interaction term on the relationship between the other explanatory variable and the response. In the illustration that we're currently working on, what we are looking at here are examples of how we would set up the linear models, how we would use the linear models. We're going to see that when we use and compare the output from these two linear models, that we get very radical changes in the predicted response given the interaction term. And we're also just going to talk about evaluation of the models, going back to the terms that we discussed before. So how we can compare them using the adjusted R-squared, for example. All right, so to recap, this data set, in this illustration, we are interested in predicting the age of a grandfather clock. Those are those like really large clocks that you see in older movies like Hook, for example. So they're like 6 feet tall, and they have the big thing that goes back and forth, right? So we want to predict the age of one of those based off the number of bidders. So how many people have basically tried to purchase the clock, and the asking price of the clock. All right, so we have two models for the same goal. We have the multiple linear regression model where y is equal to beta 0 plus beta 1x plus beta 2x. And we have the multiple linear regression model where y is equal to beta 0 plus beta 1x plus beta 2x plus beta 3 x1 x2. So the two models, we're using them for the same purpose. The difference is that the interaction model is slightly more complex than the regular model because the interpretation of the interaction term is much more difficult to explain compared, well, that's the reason why, sorry, because the interpretation of that interaction term is so difficult to explain. So we would prefer to not have to use it, but if the interaction term is beneficial to us, then we should keep it in the model. Okay, in part A, we stated each of the multiple linear regression models, right? So here we have yi hat is equal to negative 1,336.7221 plus 12.7362 x1I plus 85.8151 x2I. So this is our multiple linear regression model without interaction. The second model is yi hat equals 322.7544 plus 0.8733 x1I minus 93.4099 x2I plus 1.2979 x1I x2I. So these are the two models that we have at our disposal. And again, the goal of using the two is the same. But what we are seeing here is what multiple regression allows us to do is build a variety of models that we can compare and contrast for the same goal. All right, so we have a general model and we have an interaction model in this particular case. All right, the first thing that we might be interested in determining is, do we even need the interaction term? All right, well, one way that we can answer that question is by looking at the p-value that is attached to the interaction term. So recall that each of the p-values that are shown in the table on slide 20, they are for the null hypothesis that that slope equals 0. Okay, so this here is testing H0 beta 3 equals 0 versus HA beta 3 different from 0. Now, the only thing is the test is conditional on the other values being in the model. So the p-value here is equal to 0. So we would say since the null hypothesis, or since the hypothesis test beta 3 equals 0 versus beta 3 different from 0 gives a p-value of 0, there is evidence that the interaction term is useful. right? So we can reject the null hypothesis. So we're saying that there's evidence that beta 3 is different from 0, which would imply that it's useful. So there is a relationship between y and the interaction term. But it's useful given that age and the bidders stay in the model. So these are conditional relationships now. So we are saying we would reject h naught beta 3 equals 0, given that x1 and x2 remain in the model. Okay, so what we have now is some evidence that we should keep the interaction term. Okay, part C asks, can we remove age as a predictor? All right, so this is with respect to the interaction model. Okay, so with respect to the interaction model. Okay. So we can not remove age as a predictor if the interaction term remains in the model. Okay. Now, there's two reasons for this. One reason is that you can't have an interaction term without a main effect. Okay, so this would just be the general reason why. So if we include the interaction term in the model, you can't then knock out a main effect that's a part of that interaction, right? The second reason is that the removal of the age variable would, the right word would be, would create issues with scaling. Okay, so this is similar to the first reason, but I'm just trying to give a little more insight. First, just from like a conceptual point of view, it would be strange to have an interaction term, but the main effect term isn't a part of the model. The reason why this would be strange, well, is twofold. Like one, from sort of like a common sense, big picture point of view, you'd basically be saying, okay, this interaction term includes something that isn't present in the model. Like it's just weird that that wouldn't be there as a main effect. But the second reason, from a little more pointed point of view, would be that when you introduce the explanatory variable into the model, you provide a context of the scale on which you are working, right? So when we use our equations to fit B0 and B1, they take into account the variability in the variable that you're working with. So if we knock out the main effect, so the age value, you're creating an issue with scaling that would disrupt, I think, the predictive process. So it would make the model a little harder to interpret and a little less reliable because you're not analyzing everything on the right scales. Okay. But the general reason is just, again, if you have an interaction, you have to have the main effects, is basically the main reason. All right. Okay, in part D, it says, predict the price for a grandfather clock that is 150 years old and has 15 bidders. All right. So we have yi hat equals negative 1,336.7221 plus 12.7362 times 150 plus 85.8151 times 15. And that's going to be equal to sorry, one sec. No. Ryan, what have you done? One 860.934. Okay, and then we would have yi hat is equal to 322.7544 plus 0.8733 times 150 minus 93.4099 times 15 plus 1.2979 times 150 times 15. And that's going to be equal to 1,972.876. All right, so let's call this 1, 2. Okay, and then in part E, we're asked, predict the price of the clock that is 150 and has 16 bidders. Okay, so same idea, we're just changing the one number, but then we can compare again and we'll be able to see the effect of this interaction term. All right, so we take this, paste it down here. All right. Call this 3, call this 4. This is going to be 16. All right, so this is going to give us 1946.75. All right, and then the second one is going to give us 2074.151. All right. Okay, so let's just take a look at a few things here. So we talked about in the last lecture, where we had lecture, so last Wednesday, how the interaction term influences the slope of the other variable, of the explanatory variable that isn't being fixed. Okay, so in this sense, in this example, we are always considering 150-year-old clocks, but we're changing the number of bidders. So notice how if we take 3 minus 1, we get back roughly the slope of beta 2, right? So what this is showing us is change in bidders equals beta 2 when there's no interaction term in the model. Okay, now let's consider 4 minus 2. If we do 4 minus 2, and we've done the exact same thing, we've only increased the number of bidders by 1 unit. The difference here is now 101.275, right? And what is this value? So the change in bidders is equal to now beta 2 plus, that would be 16 times beta 3, it should be, I think. Oh, that's right. Oh well. I thought I'd be able to work this one out exactly the same way. Sorry. Well, it wasn't as clean as I hoped it would be. 127.401. There might be a mistake in there somewhere, but okay. But anyways, the point that I'm trying to make here, despite the bumbling around, when you compare the difference in the predicted price between the models without interaction, you can see that it's a linear increase. So the increase in the predicted price is directly equal to the slope. So it's directly equal to the change between the number of bidders. So it's the coefficient that's given. But when we consider interaction and we increase that value by 1 unit, you can see that the change in the predicted price is no longer directly equal to the slope that is attached to the main effect. So it's not just 93.4099 now, or negative 93.4099 in this case, but it's actually equal to, it should be equal to 127.401, which is incorporating the effect of that interaction term. Well, it's incorporating the effect of that interaction term. I really should just check these though, because there's something weird about this. It's 150. 15 plus 1. Okay, there we go. This value is off. And that value is off. Oh boy. I had them backwards. There we go. 7.5. Sorry about that. This one is the 1972.876. Wait, no. Sorry. I subtracted the wrong things. I had it all right in the beginning. 275. Okay, now we can see it. And then clearly the 101.275 does not equal beta 2, which would be the expected change if we weren't including interaction. But we should be able to figure out exactly what it is a function of. Like that's going to cancel, that's going to cancel. That gives us the 93. So it would be negative in that case. Plus. Weird. Well, anyways, the point that I wanted to make, even though it's not quite as clean as I hoped it would be in the end, is that when you include interaction, you no longer have that increase or change in the response directly equal to the slope of the main effect that you are changing. Instead, you have an influence of the interaction term on that slope variable. And afterwards, I'll try and clean this up so I can give the explanation of the exact change afterwards, because it should just be a function of beta 2 and beta 3, because those are the two values that are changing. But for some reason right now, it's not working out exactly the way that I expected it to be. But sometimes that's how things go, I guess. All right, so that's the first illustration. Now, the second illustration that I wanted to give is based off of comparing the two models. So we mentioned again that what we're trying to do here, well, that each model, so the MLR model and then the MLR model with interaction, they're both being used for the same goal. So we're trying to predict the age of the price of the grandfather clock based off of the age and the number of bidders. We can assess the fits of each model using those model utility tests that we described for the general regression model. So the model utility test extends to the case where we have interaction, or into any general case where we have multiple terms in our regression models. So on slide 22, right, so here, we have two ANOVA tables. So the first ANOVA table is for the model without interaction. And the second ANOVA table is for the model with interaction. All right, notice that these variables here for the total are the same, right? So this is just like when we compared the one-way ANOVA procedure to the completely randomized block design, which was on quiz 2, I believe. So the total sum of squares of the response variable doesn't change for either, regardless of the model we are fitting. The total sum of squares is always just basically an estimate of the squared deviations of yi about its mean. So this value is consistent for any data set, regardless of the models that we are fitting to it. Now, what we can see is that what is changing are the regression, the values for the regression source and the values for the error source, right? So for the first model, we have a DF of 2. So the 2 here represents, or this is equal to K, which is the number of predictor variables in the model. So we have 1, 2. Here we have 3 because we now have 1, 2, 3 predictors being included in the model. Okay, so the DF regression has increased by 1 given the interaction term. All right, now the influence of that, of course, is going to be that the sum of squares are going to change as well. So we have the same totals, but our regression source and our error source are changing for each model. And as a result, the F statistic changes for each model as well. So we can use this to perform the model utility test for each of the models. So in particular here we have, do the model utility tests give any evidence that the interaction term should be included in the model? Okay, so here in part A, if we were to condense this a bit, I guess we can just write it out. So if we consider the model with interaction, okay, we have step 1, H0, beta 1 equals beta 2 equals beta 3 equals 0 versus HA at least 1 beta j not equal to 0, j equals 1 to 3. On step 2, we can just test at the 5% significance level. On step 3, we have an F value of 195.1829. On step 4, we can show that the critical value, if we took the critical value approach, this would be an F on 328, 0.05. So if we pull out our F table here, 328. Okay, so here's 328, 0.05, 2.95. Okay. And then it's easy to show as well, if we wanted to, that the p-value here is going to be less than 0.05. So if we go back to the table, okay, you can see we're working with this block of numbers here. Our F value is 190, right? So that's clearly bigger than the biggest listed value. So the p-value must be smaller than 0.05. All right, so then on step 5, we would reject H0. And then on step 6, we would say at the 5% significance level, the data provide sufficient evidence that the fitted model is useful, right? So the model utility test doesn't give any evidence to reject, or it gives evidence to reject the null, which implies that at least one of the beta j is different from 0, which in general would mean that there's evidence that the model is useful. Okay, so therefore, the model utility test gives evidence that the interaction model is useful. Okay, so we have evidence that the interaction model is useful. This would mean that we should include the term in the model. Therefore, we should keep term based off test. Okay, in part B, we're now going to start to compare the models. All right. So we have evidence that we should keep the interaction term because the utility test is basically saying that the model is useful. So if there's evidence that the model is useful, that would imply that the interaction term should be, that it should stay, right? Or at least that we should keep the whole model. Okay, so is this model better than the model without the interaction term? So one way that we can answer this question is to use the adjusted R-squared terms. All right. Okay, cool. All right. So okay, so for y equals beta 0 plus beta 1 x1 plus beta 2 x2. we would have RA squared is equal to 1 minus MSE over MST. All right, so that's going to be 17,025, 1 minus 17,725 divided by 4791195 divided by 31. Okay. And that gives us 0.885. For the second model, okay, we would have RA squared is equal to 1 minus, in this case, we would have 7809 divided by 4791195 over 31. And this is equal to 0.951. Okay. All right, so the R squared adjusted values show that including the interaction term explains an additional 7% of the variation in the response variable, right? So this would also imply that we should keep the interaction term, because by keeping the interaction term, we are gaining information about the response variable. Okay, so this implies we should keep the interaction term as it gives us additional information about the response variable. Now, the only issue with this is that you have to kind of ask yourself, like, how much is enough? So in this case, we're gaining 7%. Some people might argue that an addition of like 10% would be the cutoff. Like, you want to get, if you're going to include a term like an interaction term that's going to kind of convolute the interpretation of the model, you should try and get a significant amount of information explained by that model. So in this case, we're basically saying, like, you can gain 7% of the variation about Y. So you can go from 88.5 to around 95%. Right, so that's it's just an approximation, sorry. So 0.07 equals 0.951 minus 0.885 approximately. I guess it's closer to 6.5, but that's where the 7% comes from, yeah. So but the big takeaway is just what the adjusted R squared is really good for is model comparison within the same data set. So we have two models on the same data set for the same purpose, and we want to know which one should we use, like which one is better. Okay, well, one way that we can evaluate it being better is by comparing the adjusted R squareds. But the problem with this is just that, like, how much is enough? Like, so is 7%, does that warrant keeping the interaction term? I don't know. It depends on the situation. It's a really difficult question, right? We do now have 95% of the variation in the response variable. Like, that's a lot. I mean, we're only missing 5% of the information. The model isn't overly complicated, but the interaction term is difficult to explain. Maybe it's worth not taking it. At the end of the day, what this question shows us is that we gain information. Okay, so the big takeaway here, if like just to not get too far down, the subjectivity aspect of comparing the models, is that we gain information by keeping the response. So then the natural question would be, well, what else could we do to help us compare the models? Okay, well, we could consider a statistical test for model comparison, right? And this is what we've effectively been doing the whole course. We're trying to make decisions, whether it be deciding if there's evidence that a mean is greater than some value, deciding whether there's evidence that two means are different, whether multiple means are different, whether median values are different. And now we're just extending the same idea into cases of trying to decide if there's statistical evidence to warrant saying that this model is useful to us. Well, given the adjusted R-squared comparison that we have just considered, it follows that our decision-making process would benefit from having some kind of statistical test that would allow us to compare the models. So it turns out that if we are working with two models from the same data set, and one model is a subset of the other, we can compare those two models to one another to determine if the additional terms are actually needed. This test is called an extra sum of squares f-test. So what the extra sum of squares f-test does is it says the reduced or the smaller model is a sufficient fit for the data. So the null hypothesis basically assumes that the smaller model is good enough. And then the alternative says, no, you need the bigger model. So for example, in our context, the reduced model would be the model without the interaction term. Okay, so we are assuming in the context of the problem that the model without the interaction term is good enough for the data. The full model in our situation would be the model with the interaction term. Okay. Now the reason why this test works so well in the context of what we're doing is because the reduced model is a subset of the full model. That's a requirement. So the reduced model has to exist within the full model. But because our full model only has one additional term, which is the interaction term, this test is actually going to allow us to compare the interaction term directly. So basically, we're writing a test about whether or not this interaction is needed. Okay, so we have reduced is adequate versus full required, significance level. You can see our test statistic here is simply taking values from the ANOVA table, and it's an F test statistic. This particular test statistic is distributed on DF reduced minus DF full, comma DF full. Okay, and I believe that second DF full is the error DF full. So in all cases, these are error degrees of freedom. So DF reduced equals DFE for the reduced, DF full equals DFE for the full. So all the degrees of freedom here are the error degrees of freedom. Yeah. Okay, so then basically all we're doing is running an F test with a new test statistic. But the beauty of this test again is it allows us to compare directly this full model to the reduced model. Okay, so let's just set this up and we can finish the test next class. But so on step 1, we're gonna have H0, and then we'll write it out in full. So we would have Y equals beta 0 plus beta 1 X1 plus beta 2 X2 is adequate versus HA, Y equals beta 0 plus beta 1 X1 plus beta 2 x2 plus beta 3 x1 x2 is required. Right. Okay, so on step 3, we're going to have f is equal to. All right, so we're going to have SSE from the reduced model. Sorry, SSE reduced minus SSE full divided by DFE reduced minus DFE full divided by SSE full divided by DFE full. Okay, so this is going to be from the ANOVA tables on the previous slide, 514,035 minus 218,646 divided by 29 minus 28 divided by 514,035 over 29. And that's equal to 20.726. All right. Okay, still have a little bit of time left. So then you can see if we were to take either the critical value or the p-value approach. So if we do the CV approach, we have f on 0.05, and then we have DFE reduced minus DFE full, comma, DFE full. So this is an F value on 0.05, 1, and 28. And that gives us 4.20. All right. And then it's also easy to show, again, the p-value is going to be less than 0.05 here. That's going to be for the same reason that it always is. Like if we consider just our block of values here, right, you can see that f being equal to 20.9725 falls here. Right, and that's greater than the greatest value, so the p-value is going to be less than 0.05. Right. Okay, so then on step 5, we can say reject H0. Okay, so basically what we're saying here is that the data provides evidence that the full model is required. But again, the beauty of this is that the full model is only including that one extra term in this particular case. So what this is saying is that we actually have evidence that that interaction term is useful. So at 5% sig level, data give evidence that, sorry, I'll clean this up. Evidence that full model is required. Okay, sorry, I went a little overtime. So on Wednesday, I'll review this test. This extra sum of squares F test is very useful to us, and it's something that we're going to see quite a bit throughout the remainder of the lecture set. At this point, we've actually seen everything we need for the final assignment, which is assignment 5. And of course, we've seen all the stuff that we need for the lab assignment, which is due on Wednesday. So this material, for the most part, the extra sum of squares F test and a lot of the stuff that we're going to talk about from now until the end of the semester, this is all extra. So these are things that could appear on the final, but they're not going to be tested on the assignment. So the practice problems will cover a lot of this material. On Wednesday, we're going to start talking about the incorporation of what are called dummy variables into the MLR model. So this is a really cool unit because it's, again, showing the flexibility of the MLR models. And what it also does is actually allow us to understand how the ANOVA procedure and the multiple linear regression procedure are really the same thing. So dummy variables are really what allow us to effectively construct ANOVAs from the multiple linear regression analysis. Okay, so again, I'm going to stop there. As always, if you guys have any questions, please let me know. We have our last 2 assignments, lab and lecture, due this week. And then lab final will be next Friday for everyone because the labs are on the same day. Details about that will come out tomorrow in the evening. John and I are meeting around 3:30 to discuss that and finalize things. And then we'll just have our final exam and that'll be it. So yeah, I'll talk to you guys on Wednesday at 1 o'clock.